In this section, we want to practice Taylor polynomial for a function of two variables using the following exercise. Find the approximate value of this number, square root of 0.03 square plus 2.89 square, using Taylor polynomial of order 2. At this point, we must choose a good function and a good point. A good function for this case might be square root of x squared plus y squared, because this expression is actually the value of this function at this point. X is 0.03 and y is 2.89. And then we need to find a good point. A good point means that it is easy to compute the function and the derivatives, and it is close to the point of interest. So it's a good idea to choose x0 is 0 and y0 is 3, because then the function value and its derivatives will be easy to evaluate, and 0 is close to this number and 3 is close to this one. So when we have the function and the point x0, y0, we can evaluate the function, we get the constant 3, and this allows to write the Taylor polynomial of order 0, namely 3. So that would be the simplest approximation of this value, approximately 3. But we should use T2, so let's go on. We prepare the first derivative of the function with respect to x and the derivative with respect to y. Then we evaluate these derivatives at the point x0, y0, and we get these two values, 0 and 1. At this point, we can write Taylor polynomial of order 1, namely t0 plus 0 times x minus x0, which is 0, plus 1 times y minus y0. And this can be simplified to y alone. When we evaluate t1 at the point xy, we get a better approximation of this number, namely not 3, but rather 2.89. At the end, we will compare these approximations with the exact value. If we have t1, the Taylor polynomial of order 1, we have actually also the equation of the tangent plane. Z is t1. And we can write also differential. Differential is the derivative times dx plus the derivative times dy. But fx at this point is 0, fy is 1, so the differential dz is equal to dy. Okay, to write t2, we need the second derivatives. So we must prepare these three second-order derivatives. fxx, which is f differentiated with respect to x and then with respect to x once again. And if we perform the differentiation and evaluate the derivative at the point x0, y0, we get the value 1/3. We compute the second derivative of f with respect to y twice, and we have this expression evaluated at the point x0, y0 gives 0. And then we compute the mixed derivative, f differentiated with respect to x and then differentiated with respect to y, or in the opposite order, because if the second derivatives are continuous, these two mixed derivatives, fxy and fyx, are the same. And if we evaluate this expression at the given point, we get again 0. So we have all we need to write the Taylor polynomial of order 2. It starts as t1, which was y, plus 1/2 of this derivative times x minus x0 squared, plus this times y squared, plus this times xy, and if it is 0, no terms are here more. So this is t2, And then we can approximate this value, which is equal to the function value at xy, where xy are these numbers. And f is approximately equal, this dot is important, this is just approximation. F is approximately equal to T2. And T2 is exactly equal to this, and when evaluated, we get this blue number, 2.89015. And this is done. Stop here. And if we use calculator or computer, the approximate value, but the approximation looks like that, and then the digits continue. So you can see, well, 1, 2, 3, 4, 5, almost six digits are okay. So it's quite a good approximation. The approximation is good when we are close to the point where we compute the Taylor polynomial, and when the order is high enough.